The call-outs came fast in the cockpit, practiced words spoken from memory because there was no time to look down for long. The rocket motor had just lit, and the SpaceShipTwo test vehicle lunged away from its carrier plane with a shove that pinned two men into their seats. The acceleration climbed. The vibration rose. The numbers on the primary flight display swept upward toward the transonic region, where the flight always felt rough, where the vehicle bobbled and shuddered as it tried to push through. In the right seat, co-pilot Michael Alsbury worked the sequence he had rehearsed in the simulator again and again. He had 3 jobs in this phase: call out the speed cue at 0.8 Mach, call out the trim position as the pilot adjusted the stabilizers, and then only at 1.4 Mach unlock the feather system, the twin tail booms designed to rotate upward later in the flight to create drag for re-entry. It was supposed to be simple. It was supposed to be a safeguard. But in a high workload, high noise moment, the order blurred. At just over 0.8 Mach, Alsbury made the call-out. A half-second later, his left hand moved to the feather lock handle anyway. He said, "Unlocking," and he pulled it out of the detent. Nothing dramatic happened at first. The feather handle itself was not moved. No one commanded the tail booms to rotate. But the lock was the barrier that kept aerodynamic forces from doing what they wanted to do in that speed range. In the transonic region, the loads were violent and uneven, and the actuators that normally drove the feather were not designed to hold the system in place there once the locks were released. The feather began to extend on its own. The change was instant and unforgiving. The vehicle's tail booms started to pivot upward, as if a giant hand had grabbed the back end and snapped it toward vertical. Aerodynamic forces hammered the structure. The airframe twisted. Within seconds, the rocket plane came apart in flight over the Mojave, scattering pieces across miles of desert. In the left seat, pilot Peter Siebold did not have time to make sense of the breakup. One moment he was strapped in, still riding a machine that was accelerating under rocket power. The next, the cockpit environment became a violent rush of wind and tearing material as the vehicle split into separate sections. Components that had been locked together by design were ripped apart by speed and load. The world outside was suddenly everywhere at once, loud and fast and impossible to orient to. Siebold stayed in his seat through the initial chaos. He was still attached to the parachute harness he had worn for flight, a high-altitude system built for exactly one nightmare: getting out of a broken aircraft at a height where a normal bailout could not be counted on. He later recalled trying to activate his emergency oxygen as the air rushed in, but the handle was difficult to pull, and his oxygen hose was found disconnected after the accident. Even if he had managed the force needed to trigger the bottle, the supply would not have reached his mask. What saved him was not a clean, textbook escape. It was separation. As the cockpit tumbled and the rest of the vehicle disintegrated around him, Siebold was thrown from the wreckage while still restrained. At that point, the parachute system's design became the difference between a fall and a fatal fall. He released himself from his seatbelt as he dropped, and he fell into open air above a wide, empty stretch of desert. He did not pull a ripcord. He did not choose a perfect moment. He was surviving second by second, trying to stay stable and conscious while the ground was still far below. The parachute system's automatic activation device waited for a specific set of conditions. It was built to do nothing at the top of the fall and then act at the last possible moment when the altitude and descent rate matched its trigger. When it sensed the right combination, it fired the deployment for him. The canopy erupted above the desert, a sudden blunt drag that snapped his body hard as it converted free fall into a controlled descent. He came down injured, but alive. The carrier aircraft, White Knight II, stayed intact through the event. Its crew turned back and descended in a controlled return to the Mojave Air and Spaceport, while a chase plane and range personnel watched the sky for falling parts and tracked where the biggest pieces went down. On the ground, Responders began building a map from radio calls and dust plumes because the wreckage did not land in a single spot. It carved a trail across the desert, and every location mattered, one for the cockpit, others for major structures that had separated at speed, and smaller impacts scattered between. Below him, the debris field kept spreading. The main cockpit section struck the ground hard. Other parts of the vehicle impacted across a wide area near Coin Dry Lake. Emergency crews moved toward the instantaneous impact points as quickly as they could, coordinating in a place where access roads were limited and pieces had come down across miles. No one on the ground was hurt by the wreckage. When rescuers reached Siebold, they found a pilot in shock, battered by forces no human body was built to take. He had serious injuries, the kind that came from being thrown, slammed, and then snapped into a parachute opening without warning. He was carried out for medical treatment while investigators began the slow work of turning scattered metal into a timeline. The other pilot did not survive. Michael Alsbury was found still restrained in his seat with the cockpit wreckage. The loss cut through the small community around the program because everyone understood what that cockpit demanded: precision under pressure, repeated until it felt automatic, and then executed during the loudest and most dynamic seconds of the entire flight. As data came in, the sequence sharpened. SpaceShipTwo had been released from White Knight 2 at roughly 46,000 feet. About 13 seconds later, the vehicle broke apart. The flight test data card for that run had called for the feather to remain locked until 1.4 Mach during boost. But cockpit video and telemetry showed the lock being moved to the unlocked position just after the 0.8 Mach callout, while the vehicle was still in the transonic region. Once the lock was released at that speed, aerodynamic and inertial loads were sufficient to overpower the actuators, allowing the feather to extend without being commanded. That extension drove the vehicle into catastrophic structural failure. It was not the rocket motor exploding. It was not a single dramatic ignition of fuel. It was a system being allowed to move at the one point in the flight when it could not be allowed to move, and the airframe paying the price immediately. The findings went deeper than a single action in a single cockpit. Investigators pointed to design and operational choices that did not adequately protect against a single human error, producing a catastrophic outcome, and to the reality that time pressure, vibration, and unfamiliar loads could combine into a moment where the wrong handle moved at the wrong time. For Siebold, the survival was not a miracle in the way people like to say it. It was engineering, training, and luck colliding in the smallest window imaginable. The parachute system that day worked in the one way it still could, automatically after the breakup had already happened, after he had already been thrown free. It did not make the fall gentle. It only made it possible. And when he hit the desert, the story of that flight stopped being about reaching space. It became about what it cost to test the boundary between aviation and something harsher, where a few seconds and a single unlocked handle could turn a cutting-edge craft into falling debris. Thank you for listening to Horrifying Survival Stories. Subscribe for more stories of those who faced the impossible and lived.